if they're not careful about when they heat it. But they look like that. So the first thing, without any mathematics, although I claim to be a theorist, is that they glow. They're very bright. So I'm going to first describe chemical cells. One of the original chemical cells where they saw transmutations is due to Mizuno. This is actually called a Mizuno cell. And it's not glowing very strongly, but you can see it glow. This one is part of a Naples group, Cirillo et al. And these are pictures of their apparatus, which is a Mizuno cell. And you can see that when you put a voltage across it, first, it just stands there. Secondly, the water begins to boil, but that's not when the transmutations take place. And thirdly, it creates a water plasma, and there's the picture of the water plasma, and it glows. Just keep that in mind. So again, when their cell, and this is the Naples group cell whose photographs I'm using, when that thing starts doing transmutations, it lights up the room. So sometimes in a graph, one doesn't appreciate that. And the other thing that one should appreciate is that there are so many transmutations that you can see the new chemicals with your eye. I'm going to talk about another experiment in Torino that I was happy to witness at the Polytechnic University there, where again, you can see the transmutations with your eye. We hear a lot about people having trouble seeing the transmutations. Well, you can do this or that chemical analysis, but if you look at that, you can see it with your eye. So one is that it glows, and two, you can see the transmutations, a lot of different chemicals that weren't there, with your eye. These are large amounts. The people that can only see trace amounts seem to be, well, they seem to be at conferences such as this to tell you that what they're working on doesn't happen. Again, you can see with your eye along the electrode where the different elements are forming. And when you look at the surface of it, you can see slivers of where the new elements are forming with your eye. And if you look at the tip of it, it's all scratched up. It's all indented because there have been little nuclear explosions going on in there. And if there are nuclear explosions going on there, the idea of seeing it in a nice crystal is crazy. So they explode. They deposit plenty of transmutation materials. There are enough groups that have seen this that I would say you have to be blind not to. And, of course, there are neutrons being detected. The neutrons being detected here happen to be rather slow, in my opinion. But in other experiments that I'll talk about, by slow I mean thermal neutrons or less energetic. But there are some fast ones in experiments that I will discuss at as high as 20, 25 MeV. So we had a theory for a long time about weak interactions giving you the neutrons. So what would happen there is that an electron and a proton would meet. There's no barrier. Electrons negative, protons positive, they like to get together. And if the proton can capture it, then you get a neutron plus a neutrino. And there are cross-sections for this that are well known. Actually, I'm going to give you a rather crude model where these things are just take place two bodies at a time. This crude model is due to the Rome group, not to us. But I'm going to stay with it for a while, that you can just describe this in terms of particles interacting two at a time. The actual case is there's a plasma oscillation. So you might have 1 million electrons going back and forth. And although only one of those electrons will knock off a proton, many electrons in the collective going back and forth actually contribute to what the process is. But in the simplified, and I think oversimplified model, you just take the particles two at a time, in which case you get a cross-section which depends on the wave function, two-body wave function of the electron and the proton being on top of each other. And you can work out two cases. Well, first of all, this is if you have these electrons moving in an oscillating electromagnetic field, which is coming from the plasma, these electrons get a mass enhancement. I write a few formulas because I advertise myself as a theorist, and I'll try to get back to pictures as quickly as possible. Not quickly enough. This is a simplified gas model. These are how you calculate the wave functions. And here's the one where we're back to pictures. I want to stay with this. In the Rome group of Maiani and co-workers, they used a two-body wave function in which the electron and the positron were bound. And in picture terms, that would correspond to this case where there's no plasma. For the fully ionized plasma, the electron-proton wave function has to be two that scatter off each other. And then you're in that regime. And the two results differ by a factor of about 300. And and that's why I show the pictures, since these batteries glow in the dark, you're not supposed to use the one where they're bound and they don't glow in the dark. And I believe that was the main difference of opinion between the Rome group and ourselves. The conclusions to this part is that first on the bottom, when these transmutations take place, they light up the room. They take place in a water plasma. Water plasmas are well known, a lot of industrial applications. And second is you can see it with your eye. You also have to do the chemical analysis to make it precise, but it's just blindingly obvious.